Okay, Dilhan and I were talking a moment ago. These exercises where you get to hug and kiss and all that, we're going to keep giving those to you. But then probably, I hope Monday maybe, we can deliver homework 1 and 2. Homework 1 is going to be painful. Homework 2 is going to be, let's just say, more painful. How's that? Okay. Is it the fear of pain that makes you stronger, Marmina? No, it's the actual suffering. So I need a little parental advice. Anybody out there want to give me some?
Take him to church.
Thank you. No. That one goes to church, okay? The other one, he's made a living out of watching television and playing the Wii. And
Wii's pretty good.
yeah, but whenever it's to the exclusion of everything else, that's not good. So he needs to do his homework before midnight. That's my personal favorite. And being who I am and what I project to you, you can imagine my reaction whenever I found out that he was copying things from Wikipedia and putting them into his report. And I said, John, I kill people for less than that. And he looks at me and he goes, but Tom, it's so much easier than actually doing anything. And I said, John, you're going to do this assignment over. And he goes, no, Senor Avila says it's okay. So the teacher has them go on to what's another name for Wikipedia? Somebody's bullshit, right? I mean, you don't know whether it's accurate or not. Look up population statistics on Wikipedia, and then look up population statistics from the UN. They're significantly different. Who are you going to believe? Wikipedia, of course. All right, today we're going to talk very quickly about oil, gas, and water properties. You should have had all of this in 310. This is not 310 condensed into a single lecture, but it might as well be. What do you need in terms of fluid properties? Somebody tell me, just rattle it off. You need viscosity. That's going to be a big one. Formation volume factors is definitely, a necessary condition, but is it going to be death-defyingly critical? Probably not, because it varies between, 1 and 1.3 or something. So you can just make up a number and probably be okay for liquids. For gases, of course, we'll just use the Z factor and calculate all that. But that viscosity thing, that's pretty important. Because sometimes it'll be different than you think. You think, well, it's a high-gravity oil, but it's also high viscosity. Well, not really, but it could be. And then what else do we need? GOR. Yeah, for characterization purposes, I'll say that's probably pretty accurate. Anybody else? Bubble point's a good idea. Be a good idea to have the bubble point. Okay. Anything else? The fluid gravity. Yeah, man, you guys learned well. This was McCain or Dr. Barefoot? Yeah, you guys see this stuff in your sleep. Very good. Nobody said what I'm looking for yet. Compressibility. Why has compressibility suddenly gained new importance to us? What are the units of compressibility? Well, it could be metric or it could be English. But generally speaking, the dimension is 1 over pressure. Pressure is energy. So compressibility is how much energy the fluid has. So that's something you need to think about. And for example, when we talk about material balance next week, I'll show you an example that if you take a fluid from the bubble point, let's say, from above the bubble point to 0 pressure, it would be a fictitious fluid, but you could only recover 5 to 7% of that fluid because of the energy available in the liquid. So you're going to have to do something else to get it out. Interesting. All right, so now we're talking about the formation volume factor. And you have to remember that the formation volume factor is in reservoir volume over standard or stock tank volume. Don't tell me during the test, I forgot, because it's reservoir over stock tank. Now, I'm trying to make this where an idiot could understand it, but it is a volume conversion but defined on a mass or density basis. Somebody who did not make an A in 310, tell me what that means. Mr. Beard. It's just a guess. Mr. Stone. A better guess.
Go from Reservoir Performance.
Do you remember what the dean said in Animal House? Fat, drunk, and stupid is no way to go through life. You only got 2 out of the 3. You can work on the other. Come on, man. What do I want to know? I just underlined it. It's a volume conversion, but defined on a mass basis. Me and Mr. Stone, we get along. In fact, please stop pouring your garbage in my yard. You didn't think I saw you, did you? Yeah. Anybody want to take a shot at what that means? Anybody wanted to be a chemical engineer in here? What happened? Reality? Oh, you took Chemie 204 6 times? We did have a petty one time that took Chemie 204 6 times. I think after the 3rd time you ought to be able to teach it, don't you? Yeah. Okay. So what would chemical engineers, why do chemical engineers hate us? Sorry? They're worried about Obama?
We're worried about volume.
Oh, okay. I'm trying to put the pieces together. That's all I do, okay? So we're worried about volume. So you don't buy oil in mass? What about in Kazakhstan? Anybody? What about in Russia? What about in China? How do they sell oil? By the pound? We created a convention that we sell hydrocarbons in terms of their volume. We sell a barrel of something. Now, you can have a barrel of beer, or you can have a barrel of tequila. Are they the same value? You can have a barrel of Milwaukee's Finest for $3, or you can have a barrel of Michelob for $200. Which are you going to choose? They have differences, right? So everybody has their own recipe for how they assign a value. We have standards. What are the 2 standards? West Texas Intermediate, Brent Crude, and what's the 3rd? Saudi Light, usually. Okay? But all of the other prices are based in terms of quality as higher or lower. You'll hear them referenced, plus or minus Brent or West Texas Intermediate, etc. I kind of got off on a tangent here. But they want us to work in terms of mass. Dylan, Muscat's book, best book ever written, full of homogeneous fluids. The equations in there, are they in terms of volume or mass? Mass. Why is that? Because Muscat was a physicist. The greatest the greatest petroleum engineer that ever lived was a physicist that stood about this tall, and he didn't have a computer. I'm not looking at Dylan, okay? Because Dylan does have a computer, but he didn't have a computer. If Muscat had had a computer, we wouldn't need you, because he would have figured out all the problems that were to figure out. Interesting. So you have to recognize when you're going to transfer from one system to another. But we're going to make that easy. Everything we do in petroleum engineering is going to be in terms of volume. Maybe, I guess, if you start dealing with steam or something like that, you'll go back to mass. But for the most part, it'll be in terms of volume. Typical values of the oil formation volume factor, Mr. Stone. 1.2, kind of dead. 2.4, really spongy. That's a volatile oil. You'll never see an oil formation volume factor in your practice probably over 1.5 or 1.6 for a black oil. Okay, then gas, these numbers are meaningless because they're, we never look at them per se, but these can be pretty small. I like to report the gas formation volume factor in barrels per MCF. It's just a personal choice. That way you can convert the rate to barrels automatically, but you don't have to worry about that. Water, The water formation volume factor is really just 1, so we don't have to worry about that either. Any other questions about the formation volume factor? So when we give you a homework assignment where you are given some equations and you have to program all this in Excel, what's going to happen? We'll get Billy to do it and then we'll copy. No. Read the honor code. That won't be that kind of assignment. You're going to have to program these equations in Excel and create a worksheet to calculate the fluid properties based on certain inputs. Who wants to take a shot? Miss Leva? A shot of Milwaukee's best, okay? Who wants to take a shot at what the most difficult part of that assignment will be? That's good. Hold it. You got to hold your breath until we get to it, okay? Let's see. Take a deep breath. No, she's not going to do it. I can tell. All right, so the next thing we have to talk about is viscosity. And I stole the words here from a slide I saw one time where someone said that viscosity is sort of an internal friction. And we know that we're going to have to use some mechanism to calculate it. Oil viscosity, for what we're going to look at, ranges somewhere from 0.2 centipoise, very light oil, significantly less viscous than water, up to about 30 centipoise. Our Kazakh friends, where are you at? Right here, right? Yeah? Okay, so when you go to the west part of Kazakhstan and you start looking at some of those old reservoirs, what's the viscosity of that stuff?
Pretty viscous.
Pretty viscous, yeah. It comes out looking like black shaving cream, right? Yeah, it's more solid than it is liquid. And it's as high as 1,000 centipoise. Okay? Where's our Canadian buddy? He probably dropped the class. Oh no, this is in the other one, sorry. Anybody from Canada here? No? There's some reservoirs in Canada that you actually produce the reservoir with the oil. What does that mean? It means you better have real good sand collection facilities. So if you owned a property like that where you were going to collect 1,000 centipoise oil and a whole lot of sand and water, what would you do? How would you construct your facilities? No, you'd have 2 of them. And whenever one of them fills up, you take a big switch and turn it over to the other one and clean the first one out. That's exactly what they do. Gas viscosity, again, you're never going to see it. It's just really low. It's going to be a calculation that we make. Water viscosity, since water's the basis for the centipoise, approximately half to maybe a little bit over 1 centipoise. And the reason that it's a half is it's at temperature and pressure. So, any questions before we leave viscosity? This is all first grade reader stuff, I know. All right, here's where we get away from the first grade reader. Here's the definition of fluid compressibility. And most of you are saying, well, we all know about this part, but you see, you forgot about this part. And this, of course, is for pressure, what? Less than, greater than, less than the bubble point. Okay? And this term is for all pressures, but it's usually the part that, of course, at the bubble point, the solution gas oil ratio at and above the bubble point, this term goes to 0, so we don't have to worry about it. I just wanted you to think about that. What do you think happens to a function when it has a switch? Anybody? Sorry? An asymptote. It jumps. Okay? And that's exactly what's going to happen with compressibility. Gas compressibility equation, is it complete? Or is it missing something? It's complete. Okay, this implies that we have a term where gas is coming out of oil and where gas is coming out of water, but gas is gas. I guess we could have oil coming out of gas, but that's not going to be included in this discussion. Okay, so now we're going to fall back on a discussion of units, and in particular PSI reciprocal, and we're going to refer to this in terms of 1 times 10 to the minus 6. These will be the so-called microsips that you hear. The minimum oil compressibility is probably about 5 for an oil above the bubble point. The maximum is probably about 20 times 10 to the minus 6. The minimum for an oil below the bubble point is probably about 30, and then the maximum, it could be as high as 200. Now, if we were doing something 1-to-1, okay, the minimum value below the bubble point is 30. The maximum value is 200. If you divide 200 into 30, you get something over 6. So you're going to have 6 times more energy available to move fluid. Okay, I'm beginning to understand this. Gas, on the other hand, is very compressible. You can tell. Ow. Okay. Water is essentially incompressible. So guessing will not hurt you here. 3 to 5 times 10 to the minus 6. Now we've got a pesky little problem that's reared its ugly head recently, and that's formation compressibility. Why would formation compressibility be an issue? And we'll talk about this some more when we get to material balance. Marmina? If you had another brain cell, it'd die of loneliness, right? You like that, huh? He's not the one who kissed the street, though. Okay, so why is formation compressibility suddenly become so important to us? And us can mean U.S. if you want. You didn't like that, did you? Who's your worst enemy in here? You. Yeah. That was quick. All right. Who wants to volunteer on this row to help me out?
It's going to decrease your porosity.
Okay. But more importantly, how does this occur?
When you take fluids out.
Okay. When we take fluids out, we remove part of the structure. You're not thinking about it in this way typically because we always think that the rock structure itself supports the overburden. But in a poorly consolidated rock, the fluid is supporting the overburden, and the rock is very compressible. How does that happen geologically? And you don't have to give me the 7 theories. Just tell me what you think. You want me to move up? Who's your worst enemy? Oh, you're a lover, not a fighter, huh? Okay. How about on this row? Where's Loco today? Ah, there you are. I notice you're always last. Yeah. You almost got hit by a car this morning, too. I saw that. Or was that yesterday? Was that yesterday or today? When I saw you in the street, Rain Man. You waved at me and said, hey, what's going on?
Well, I didn't see it.
But you saw me. So how can geologically this happen? No habla English? Anybody? How can this happen? Geologically, how can it happen? Somebody tell me. Blah, 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 blah. Try again. Sorry? How wrong is that, Marmina, on a scale of 0 to 10? It's about 100, okay? Okay, good guess, Adam. I like good guesses. Actually, that was a terrible guess, but it's the other way, right? It's that there was so much material deposited so fast that it didn't have time to turn into rock like we think of. Now, where would that happen? Around here. Very good. And how long has stuff been coming out into that gulf? millions and millions of years. In fact, if you look at a satellite photo, you can still see stuff coming out. It's being regenerated right now. So what happens is you have very rapid burial. You don't have very much time for this stuff to come to equilibrium. And actually, Adam's got a point, because if there is a theory that says it's the hydrocarbon generation itself that's in contact with the reservoir, the shale below it or the shale above it, ejects the fluid into the formation. And because it has nowhere to go, it's at a very high pressure. So actually, he wasn't as wrong as I implied, although he wasn't thinking that, so technically he was as wrong as I implied. All right. So now we've got these abnormal pressures. Why does anybody care about abnormal pressure? Could you shake his head and see if that one's still in there? All right. Yes. But I was trying to think about, G money, that kind of thing. If you have an abnormally compressive system and it's overly pressured, what's going to happen when you depressure down to the point where the rock collapses? It's abnormally pressured, which gives you an apparent volume that is not correct. It appears to have much more fluid in it than it does. It's like overpumping a bike tire, for example. So what's going to happen? When you produce this thing down to a certain point, then it becomes normal pressured or subnormal pressure. The formation may even collapse, and you're going to have what happen? That's the end of the story. Somebody work offshore this year? Anybody? Where?
South of Venice.
Could you give us a little more detail?
South of Venice, 12 miles.
Oh, so you're in shallow water. From this point on, your name is Larry, Curly, and Mo, okay? All right. Anybody work deep water? Name a deep water field. Okay. Are they doing water injection at Tahiti? Anybody? How much does a deep water well cost? About 100 million, right? Okay. And what would you like to get out of that well, Mr. Zanero? At
least 30%.
Mo money, right? So now, if you're going to turn that well into an injector, how long is your career with that company going to be? Yeah, better warm up the resume. But ironically, BP realized that when they discovered Thunder Horse, that it is very highly overpressured, and that if they do not inject water to support the overburden, the reservoir will collapse. So you're seeing people drilling $100 million injection wells now as part of their development plan. Incredible, huh? All because of this. I mean, it's a little more complicated than that, but you can say you heard it here first. And maybe you'll stop somebody from doing something stupid. Okay, we got to pick up the pace. Dilhan's starting to get nervous. All right, I'm going to skip this except for, did I have a zoom in on that? No, that's in another presentation. Okay, I need you to look at this. This is the logarithm of CO. This is P greater than PB. This is P less than PB. So we have a profile over here, right? And then we have a profile over here. Okay, Larry, what happened? Okay, so we're looking over here, and we're going to give Larry a softball, right? DRSO dP right here is equal to what, Larry? What's the derivative of a constant?
Zero.
Don't help him. All right. So over here, this term does not affect the calculation, right? Now, when we get over here, what's the derivative of something that's not constant? I don't know, Tom, but it's going to do something, and that's exactly what it does. It causes a jump. And how big is the jump? It's big. Fortunately, this phenomenon happens very well in the lab cell, and it does happen in the reservoir as well, obviously, but it happens over a large space, so you're probably not going to see some kind of giant effect. It's just a unique characteristic that we have to be aware of. Now, anybody who wants an A in this course has to tell me why the viscosity is a minimum at the bubble point. Mo?
Because it just absorbed all the gas and hasn't started becoming overpressure.
It's pretty close. You don't want to give him it or make him earn a little more?
Good.
I think Miss Sleva, sweet on you. She says give it to you. Huh? How about $20 and you guys don't come back? You know? No, I mean, I'll buy you lunch. You know? Why are you turning red? Did I actually discover something going on? Okay, Miss Sleva, let's help him out here. I forgot what the point was. What was the point?
Talking about viscosity.
Okay. You going to help him realign that thinking? Okay, so when it's over on the far right-hand side, all the molecules are compressed. You want to, let's do a demonstration. Come on, Mo, Larry, and Curly. All right. Get in between here. Come on, hurry up. Get your hands out of your pockets. Jeez. Come on. Okay, your molecules. You cannot bounce past, there's an imaginary boundary. I'm a piston, okay? I want you to bounce around, but you can't go past here and here. Here, I'll get Mr. Cottle. I want you to lay on the floor. Come on over here. I want you to be the barrier. So, bounce around. Okay. And so now we're increasing the viscosity, right? Because they're pounding it. Now I'm going to let go here, okay? All right. Now keep bouncing around. Now this is a really hard part. I need some gas to come out. All right. You guys did fine. All right. Now does everybody understand how this works? You guys are going to miss me when I'm gone. I'm telling you that right now. Okay, we'll forget about that. Now we're going to talk about the Z factor. Oh, this was tailor-made for you. Come on, Z. Tell us about your factor.
What do you want to know?
We'll try to start at the beginning, will you? Somebody's homework doesn't have a staple, Mr. Moss. Anybody want to loan Mr. Moss a staple? So tell me, Dilhan, what's the penalty for a no stapler? Zaniro has a nano stapler. Oh, that's pretty good. Okay. So Zaniro, you ready? This is important. Why is it important, Miss Leva? Because this is the worst part of the calculation. This is the one where you got to know the answer to get the answer. It's like a Chinese finger toy or something, you know? Okay? So this is Z, and this is pseudo-reduced pressure, which is pressure divided by the critical pressure. And this is TR, which is the temperature divided by the critical temperature, okay? Now, who haven't I tortured today? Mr. Moss. Mr. Moss, I know your ambition was to be a chemical engineer. Unfortunately, you washed out, and you're here now. So what I want to ask you is, do you think that this line is uniquely defined by data? I know I didn't draw it very well, but the 1.6 isotherm. You think if we went in the laboratory and we took a gas sample and we measured the Z factor, we measured the expansion at temperature and pressure, could we reproduce this line? 3 options, Mr. Moss. Ready? Yes, no, maybe. Okay, now you have to explain maybe. Good luck. No, it doesn't. Why doesn't it matter? You failed. Now, what kind of person would have somebody's father's number in their phone and make a little call? You okay?
Yeah,
You want me to do it later?
you call later.
Yeah, okay. I'm glad we're down with that. Oh, nice hat. Mine now. Okay, so can we reproduce the 1.6 isotherm in the lab? Mr. Moss says maybe, right? But then he got the maybe why wrong. He said maybe we could do it if we reproduce the experiment perfectly. Why is he wrong, class? You all had this before. Somebody. Sorry? Can you speak into the microphone?
Those are pseudo-reduced values.
And that's important. Why?
Well, they're not actual, so you can never observe them.
You failed too. Come on, think, people.
Depends on the composition.
All right, more. Zanero was onto it. This particular chart was created for pure components, right? Standing in cats, sat down, and they took the Z-factor data available at the time. What would be a good material to have Z-factor on? Yes, gas is a good idea to take the Z-factor. What material? Not what state of the material, what material? What do we sell? We sell hydrocarbons, okay? What hydrocarbons do we sell? We tend to sell paraffin hydrocarbons. Can somebody please recite the paraffin hydrocarbon song for me? Methane, okay? Ethane, propane, butane. You got all these memorized now? All right, so if I plot them on this plot at an isotherm of 1.6 and using Mr. Moss's magic device, I have made perfect measurements. And using Mr. Zanero's, he said pseudo-reduced, but it's actually just reduced, although we're representing as pseudo-reduced because we're going to use it for mixtures, but we're not going to talk about that now. We're going to talk about pure components, okay? So, it's only pure components. What's the methane line going to look like? Let's say that this is methane. What's ethane going to look like? The same thing. Not exactly. It might dip down a little more and come up. I'm drawing this kind of badly. Okay, and this would be ethane. Okay. And then so on and so on. Why aren't they exactly the same? Sorry? They're not the same, he says. That's why they're not the same, is because they're not the same. This is geometric logic, man. I think you just put yourself in an infinite loop. Anybody else want to help me? Why are they not the same? Louder. Everybody scream at once. The answer, okay? The law of corresponding states says what? What does it say? I'm going to throw your eraser at Dilhan if you don't tell me. Somebody take a shot. Mr. Moss, it's redemption time. I think what you're really trying to say is it has something to do with the definition of the pseudo-variables, whereas we can define a density at a particular critical pressure and a particular critical temperature and temperature, properties can be related. Isn't that what the law of corresponding states said? Something like that? So what happens when you break the law? Oh, Mr. Cottle wouldn't know. Anybody else? Yeah, I realize that's your favorite second home, but I'm trying to think of what happens when we break the law of corresponding states. You're going to leave here today with a couple of pieces of knowledge you didn't come in with. One is that this chart is somebody's interpretation. It's not reality. Yes, there have been equations fitted to it, and for all you care, that's all that matters. But the data that was used to make up this chart back in the 30s and 40s was plotted on a graph, I'm told, something like 9 feet, and they paid somebody to go around plotting each point. And then they went in, and they took a curve and drew it through the data. They created it that way. And then somebody went back and read all the points off. It's in a paper by Potman if you'd like to see it. So this is the basis for all things we do in gas reservoir engineering. And it's wrong. What's next? How wrong is it? Nope. It's not very wrong because A, the correlation worked. The corresponding states thing, it's in the right area. Okay? But why also does it not matter? You're never going to hear me say it doesn't matter again, but it doesn't matter. That's okay because we smoothed it out. You know, if you go above propane, I think the thing really starts to break down, but we're dealing with, this is for gases, so probably we're looking at methane-like mixtures, so we're okay. But why is it okay?
The magnitude of the error that is less than the magnitude of the error.
That's a good answer. It's not the one I was thinking of, and it's really not the one I want, but that is a good answer. So you get the Lucas Moss Award for the remainder of the day. Guillermo, why doesn't it matter? Because we all use the same chart. And if we all use the same chart, it doesn't matter. Now, of course, I'm lying because people use equations of state, people use other things, but for the sake of argument, it doesn't matter because we all use the same chart. Now, who wants to help me out with this? This is, again, the z-factor, and this is pseudo-reduced density. And I'm sorry, I don't remember the definition off the top of my head. But what is in pseudo-reduced density? What is it a function of? Dilhan? Number one, it's a function of pressure, temperature, composition, or molecular weight. Very good. How about a hug? No, I guess not. Okay, Mo, you redeemed yourself. So if it's a function of z-factor, and Ms. Lever, we have the z-factor on the y-axis and the z-factor in a variable on the x-axis. Is that good? Bad? It's stupid. Oh, Mr. Stone, I accept your challenge. So z is a function of pressure, temperature, molecular weight, right? And that is equal to a function of what? The pseudo-reduced, well, we'll write it out. What's your favorite kind of equation, Mr. Stone? A0 plus A1 pseudo-reduced. Yeah? Plus A2 pseudo-reduced squared plus A3 pseudo-reduced cubed plus ... Is that going to work? Sorry? No, it's not infinite many terms. This is an equation of state. This is a Benedict-Webb-Rubin form of an equation of state. This is why I hate chemical engineers. They figured this part out, but then they didn't tell us how to solve the damn thing. How do you solve it? Iteration. What's that called? Successive substitution. It's sort of like you taking this class until you pass. You like that? That's iteration 2. Is there a smart way to solve this equation? Do good guesses. That's good. Anybody else? Mr. Lever, you're not talking to me anymore. Am I going to get another memo from the Vice President for Student Affairs?
What was the first one about?
For the exam last year. Yeah. Got called over to the dean's office, you know.
Okay, you're still doing it?
The dean told me I could do whatever I want, that we're not educating romper room kids over here. We're the #1 department in the country, and he's not going to question my methods. That's pretty cool. It was not what I expected, people. I thought I would be taking very early retirement, but so bring it. Anybody else? So how do you solve an equation that has a variable on both sides again? Iteration. So maybe we'll give you what's those things called, Dilhan? Sub, root, that thing, that program thingy, and we'll do that for you. Okay. All right. Now, what about that viscosity thingy? Way back in the good old days, and this is not John Lee, this is some guy that was worked for the Gas Technology Institute at the time, and they came up with this equation that looks like this, and the parameters for it, or the coefficients, are over here. So they made this really ugly equation to solve for gas viscosity. It's a great equation. It's being used right now, I'm sure. What's wrong with it? It was created from a relatively small number of points, only 8 gas samples, and I think the maximum pressure was less than 8,000 psi, and the maximum temperature was like 220. What's the hottest reservoir temperature you know of yet? 500? Where's that? There's nothing 500 yet. There's some 425, but we'll get there. Be patient. What's the highest reservoir pressure that you've heard of so far? 25,000 is the highest I've heard. Okay. So this correlation is probably not going to work for that. What's the bad thing about when equations fail? You don't know, because it looks just a number. It doesn't make any sense to you. So what we did is we went back and we refitted their data and a bunch of other data, and we came up with a new sort of equation of state for viscosity, and I put it here, but don't worry. This equation's simple. Ms. Leva, for the purpose of redemption, will you tell me what the missing link is in this equation? Sure you do. Right there, density. You got to know density to get gas viscosity. Okay? Why don't we need to know density to get oil viscosity? Well, it's correlated differently. It is a function of that, and there are some density-based correlations. But for the most part, we don't need to do that. But for gas viscosity, they've been doing this since the start of time. This is, again, our chemical engineering friends. How do you get gas density? Anybody? Guillermo, you still awake? Okay. Loco, how do you get gas density? How about here? Is that how we get gas density? Yeah, thank you. We get it from the Z factor. Okay, we talked a little bit about your take-home problem. It was an exercise, right, where they derived the steady state equation and assumed that the gas viscosity compressibility factor was constant. Is that true or not true? It's not true. Okay? But for pressures less than 2,000, it appears to be true. How many reservoirs are there in the world with pressures less than 2,000 psi? Not a whole lot. And it has to be less than 2,000 psi the whole time, right? In order for this to be valid. So this is sort of ancient history, but I wanted you to be aware of it. And then this is the one that's going to be really confusing. If we start looking at gas viscosity and gas compressibility product, there are certain rules or certain requirements that it'd be constant. For a liquid, we will assume that the viscosity compressibility product is a constant. For a gas, will we assume the same thing? 3 options. Yes, no, maybe. What's your answer? Let's go to the data. From this view, gas compressibility multiplied by gas viscosity, there appears to be a constant as a function of pressure if you ignore all this. How many people like that idea? Nobody. Now let's look at exactly the same data plotted on a log-log scale. This is 1 to 1. Johan, what does 1 to 1 mean? If I take a marble out, I got to put a marble in, that kind of thing. So this says that gas compressibility times gas viscosity is equal to some constant A divided by pressure or multiplied by 1 over P. Is anyone here willing to make the hypothesis that Y is equal to 1 over X is somehow constant? No. It's almost what one would call the most unconstant thing there could be, unless, of course, it was exponential or something else. This is not good. And this is going to come back to haunt us whenever we start looking at well tests. Now, you're never going to have to worry about this because in the class, we're going to take care of it, and in the real world, the vendors are going to take care of it with software. So the limitations of black oils. Some people say we shouldn't be using black oils for certain kinds of depletion systems, but I'm not going to worry about it. It'll be okay. We can use constant properties for liquids, probably 99% of the time. Now, when you start getting good at software, you're going to find that one of the vendors in particular has a reservoir simulator tied to it, and you can start changing anything you want. Is that a good idea? No. Because the whole purpose of this class is to teach you to diagnose, to analyze, and then to model. If you jump straight to model and you match anything that comes your way, you have proven nothing. This morning, Dilhan, we received a well test from a very good friend of mine. His estimate of permeability was approximately 1 millidarcy, and he was patting himself on the back. Unfortunately, that is a well-known reservoir of permeability 0.001 to 0.005 millidarcies. And when we forced that permeability on it, we got a much better interpretation, and we went about our way. He is not a well test expert. But if he gave this analysis to someone and said, with his stamp of approval, the permeability is 1, how many consulting jobs do you think he's going to get? Probably a lot, because nobody knows any different, okay? That's why I'm trying to teach you. You're going to come up with situations which are in conflict, which there's no unique answer for. How did we resolve it today? By tying what? The pressure transient history and the production history, both of which were garbage, by the way, just for those of you who want to know. The limitations of using a dry gas, this isn't really going to be a limitation except for gas condensates. And then the question about existing fluid properties. We're going to give you certain correlations and expect you to generate a program. You can take other correlations and put those in there. Right now, the literature probably has the most complete correlations for what we're going to run into in the near term. The stuff at ultra high pressures, a friend of mine with a major independent sponsored some research at another university where they generated Z-factor plots up to 25,000 psi, up to 450 degrees Fahrenheit. Why did they do that? I'll let you go if you can tell me why. Why did they do that? What's your number one enemy as a contaminant?
Sulfur.
Sulfur. Good guess. Wrong. As a hazard at the well site, yeah. Water. How'd you know that? Simple man, simple answer, huh?
Exactly.
Okay, so tell me how water is worse than everything else.
As soon as you start flowing it, it's going to want to flow more than the air.
We're talking about the Z factor. Okay? Right answer, wrong question. Okay? Ms. Leva, you want to re-engage, or you're tired, huh? It's time for a nap. Anybody out there in Wonderland want to take a shot at this? Sorry? No, I need a chemical explanation. It is a vapor, and you're getting warm, no pun intended. What kind of molecule is water? It's a polar molecule. All the other contaminants are sort of like hydrocarbons. CO2 is kind of like a hydrocarbon. H2S is kind of like a hydrocarbon. Nitrogen is not like a hydrocarbon, but its molecular weight and density are kind of like ethane, I think. But what's wrong with water? It's a real outlier. When you start looking at water's critical temperature and pressure, it's off the scale. And so all these times that you've taken water for granted, especially water vapor, when you start getting into ultra-high temperature and ultra-high pressure gas reservoirs, you better get a sample. You better take it to the lab. You better find out how water affects those properties. Why? Remember the discussion we had about abnormal pressure? Abnormal pressure can cause you to make a very substantial error in reserves estimation. And contrary to what your boss told you, making an error in the company's favor is not a good idea. What happens with abnormal pressure systems is you will project an estimate of reserves which is perhaps twice as high as the real reserves. Okay? That might get you a promotion, might get you a raise, but it's going to get your head in a bucket sooner or later. And I think water is going to do the same thing. Water has a nasty effect on our ability to perform reservoir engineering calculations. For the rest of your career in this class, we're not going to worry about water. But water is sort of the 1,000-pound animal in the room that nobody's thinking about. And the higher the temperature, the higher the pressure, the more it's going to affect us. The lower temperature, lower pressure stuff, probably not. Ms. Leva, you want to close the day? What's the word for the day to close? Quiz on Monday. I heard it. Is that what you said? Okay, Dylan's going to show you the exercise.